So you can pull that off the chat. And Dr. Carlina's also, I'm not familiar with that one. I'll have to take a look at that one. All right. So TensorFlow is especially for neural networks. I don't know if they use the other machine learning techniques in TensorFlow. I think it's especially for neural networks. So as Charlie said, there are many different algorithms for machine learning. I just want to make clear that the different algorithms that he presented are very valuable and are good for smaller data sets. The neural networks is really only good for very large data sets. And one of the mistakes that is often made is to apply neural networks to small data sets. And as Charlie showed, in his data set, the neural networks perform very poorly. And that's quite usual. So what I'm talking about now is really only one aspect of machine learning. Those other algorithms like random forest or a support vector machine or k-nearest neighbor, those are also extremely valuable tools. And the fact that in Charlie's method combines several of them, that's also a very active area of research. You try to get the best of all possible estimators. There's a lot of possibilities in there in areas of research. So again, so what I'm talking about now is specifically about neural networks. And as I said before, this tutorial follows one of the most famous examples of an application of neural networks, which was digit recognition. This system is actually used in the US Post Office now to address mail. You read the mail and the machine will automatically find the address and send it to where it's supposed to go. So all right, so I'm at this place. I'm going to run Google Colab. Let me stop this and we'll start again. Okay, so we'll just run this, and that means I'll have to load TensorFlow again, and I hope it's large enough for you to see. All right, so here, so Keras is kind of the base language for machine learning. That's a Python library. This is a Python library that has machine learning operations. So in this case, you're going to build a neural network that classifies images and then train the neural network and then evaluate the accuracy. Okay, so let's go down and see. All right, so I mentioned that the first thing you need to do is to import TensorFlow, which has the neural network operations. So I click here to import TensorFlow, and it should be coming shortly. I don't know if it's finished or not. Okay, I think it's already loaded. I think this one may also be done. Let's go ahead and do this one. All right, this one's done. Okay, and I showed before that you can show the image. So let me just do that quickly again. Show you that each instance in XTrain is a digit, is the representation of a digit. So I'm going to import a matplotlib, and here it is, matplotlib pyplot as PLT, and I'm going to do plt.imshow, and then I can just choose some XTrain, and I'll just take one. I'll take 345. And let's see. So first I'll print ytrain of 345, and then do the imshow, and let's see what happens. All right, so you can see what it looks like. It looks like a 1, and in fact it is a 1. Okay, so the machine is going to be trained to recognize these images. Now you can see that this is not an easy task because this also looks partly like a 7. So the machine has to be very smart. All right, so here we're going to build a neural network. So here it says use sequential by stacking layers. All right, so what we have here is a neural network with actually it's 3 layers. So maybe you can recognize some of the things that I mentioned. This one here, maybe I can try to diagram this to show you what's going on with this. Right. These are common configurations for layers, and it would be nice if you could see what's going on with this. So let me start a new page. So this is identification, and then let me go ahead and paste this in. All right, and let's see what this is talking about. Okay. All right, now first one, the one that says flatten and input shape. All right, so what is this talking about? Let's see, is this working? Let me try the other one. Oh, neither one is working. Here, let me unplug and plug in. Okay. Not this one. Let's try this one. Okay, good. All right, so I'm going to look at this flatten here. First, we have input shape 2828. What you have is an image of pixels. So here's my image. And you can see from this picture here, if I go back here and you see what it looks like, you can see that these are squares. Each one of these squares is a pixel, and each pixel is one particular level. And if you look at how this is done, the level is scaled so that the level is between 0 and 1. All right. If I actually print X-train, you'll see that. Let me just choose one. Okay, and you'll see that these values are all scaled between 0 and 1. Okay. The larger value means that the image is darker. The zeros mean the image is light. I should say that the IMSHO I showed, the blue areas were actually white in the original image. So I hope you're not confused about that. People didn't write in blue. The blue areas were actually white in the original image. And this 0.99, for instance, that means that the image was very dark there, very black. Okay. So we have an image, and this image is divided into pixels. And each pixel represents one value between 0 and 1. Now it says 2828. That means that this is a 28 here and 28 here. Okay, so 28 pixels by 28 pixels. I don't know if I can count, but I think that if you count here, you'll find that it's 28 across, that each one of these has 28 entries. Each one of these square brackets has 28 entries. Okay. Now flatten means that you take all of these 28 by 28. This is going to give me 250. What is 28 times 28? It's not 256. It's more like, well, let's find out. If I take 28 by 28, that's 784. So there's 784 pixels. And what flatten does is it puts all 784 pixels in a row. Flatten takes this image and just lists the pixels one by one, from 0 to 1, all the way up to 784. So these become your 784 inputs. as Charlie mentioned, this is the interface with the real world. This is what's coming in from the real world. And each one of these numbers is going to be a number between 0 and 1. Right? So that's what flatten does. All right, now then we have dense. Okay. So dense means, what dense means is that there are lots of connections. And this 128 means that's the number of nodes, or that's the number of outputs that come from this layer. So here we have 128. So here we're going to have 128 of these. And dense means that every one of these is connected to every one of these. Okay. They also call this fully connected. Right. So there are many, many, many connections here. In fact, if this is 784 and this is 128, the number of connections is 784 times 128. So there are many, many, many connections here. Okay. So you have many, many weights. 784 times 128 connections. So my weight matrix, because there are 128 outputs and 784 inputs, that would be 128 by 784 matrix. Okay. So all of these numbers need to be trained by your neural network. Right. All right, so let's see what's next. Okay. This activation function is a nonlinear function that's applied to the output. Okay. So the ReLU function, you can look that up on the web, but the ReLU function means that the outputs here, so your 128 outputs go out, and each one is passed through a ReLU function. That means that this output is passed through a function that looks like this. ReLU function looks like this. It's flat here and then up like that. So every one of these outputs is passed through this. Now what this does is, if the output is negative, which it can be since weights can be negative, then it's set to 0. And if the output is positive, then the value goes through unchanged. One way to express ReLU, which my students may recognize, is that ReLU of x is equal to the maximum of x and 0. That's the mathematical definition of ReLU. Okay. Now each one of these outputs is subject to the ReLU function. So we have 128 copies of this function. Okay. And there's also a bias, which I think I want to pass by that detail because well, all right, bias will shift this function to the left or to the right. So that's what I should say that there are also 128 biases. Okay. For the ReLU function. All right. So far we have, as Charlie said, this is what would be called a hidden layer. We have this one, which is the input. We have this one, which is the input layer. We have this one, which is the hidden layer. And we have this, which is not a layer, but this is for training purposes. And I think it would take me too long to explain this, but this dropout is a training technique. And it makes your model more well, the technical word is robust. It makes the model more robust, which means it's less likely to make errors. All right. All right, then we have one more layer, and this is dense layer. So what happens is that these 128 outputs, so let me reproduce the 128 outputs here. And these get narrowed down to 10. Okay. Now, why are you narrowed down to 10? Because there are 10 different digits that we're trying to classify. Each image that comes in should be attached a label that's 0, 1, 2, 3, up to 10. So these are the output values. Okay. And because this is dense layer, every one of these 128 is connected to every one of these outputs. So these are all connected, lots of connections. Lots and lots of connections. So you can see that before computers, this would be unimaginable. And every one of these connections gives me a different number that I need to optimize. All right. So these are my different output values. All right. Now I haven't really explained how the output values relate to the output that comes here, but we'll get there. All right. So that's the structure. If I wanted to summarize this structure again, you have your image, your 28 by 28 image. This gets flattened out to, what was it, 786 or something like that? 786 values. This was fully connected to 128 values. And these are fully connected. Okay. And then we have 10 values here. And these are all also fully connected. Okay, lots of connections here. And then you have the outputs. Okay. And then we use the outputs so when we have, as I said, we have labels from 0 to 10. Okay. So we really have three layers. These are fully connected here. I'm sorry I don't draw very well, but I think you can compare this to, well, if I take a picture of a neural network online, or if you remember Charlie's picture of a neural network. All right, so something like this, something similar to this, we do have 3 layers, although here instead of 3 we have 786, here we have 128, here we have 10, and we're not going down to one single entry. We only have 10. Okay. All right. Yeah, so this is 786. Yeah, 128, and then goes down to 10. All right, good. All right, so let's see how this works. Let's go back to the, I think we're here. We're here. Okay, so let's go down and see what it's going to do next. What's going to happen next? All right, so I've explained all of this. I didn't really explain dropout, but I did mention that this has to do with the training. All right, now, here it says, for each example, the model returns a vector of logits or log odds scores, one for each class. Now, there are 10 classes because there are 10 possible digits. And here they have this. I think I didn't execute this one yet, so let me make sure it's executed. I think it's done. All right. Now let's see the output that this model gives me. Now this is an untrained model, so it's not going to give me very good results. And here we're just giving the output for one particular image. This is actually the first image. I'm not sure why they did it this way. I would just put in a 0 here, but let's try this. All right, so maybe I didn't do this right. Why is that not correct? Okay, so let me do this. Okay. All right, now, what do we have here? These are my outputs. And here we're getting back into some statistics. So here's a sample output. Whoops. Here's my sample output. Now I wish I could talk with people individually because it's hard to, I think I can just go over quickly what this means. Here we have 10 numbers. Okay. Now what you want to do is you want to associate these 10 numbers with a probability. Okay. All right, now, so when we have these numbers, but these numbers are negative. Now probabilities are between 0 and 1. So somehow we want to associate these numbers, which are real numbers, we want to associate them with a probability which is between 0 and 1. Okay. Now one way to do this, there are actually two common ways to do this, but one way to do this is called the logit. Is to use what's called logit or log odds. Okay. Okay. Now the odds of an occurrence with probability p. I don't know if you have any gambling in Nigeria. I'm sure you do. But in the US, people gamble on sports games or they gamble on horse races. And they will always report the odds of someone winning. Now, the odds of an occurrence with probability p is defined as p over 1 minus p. Okay. All right. Sometimes people will say the odds are 1,000 to 1. And that means that you have, so that means that you're very, very likely for it to happen. Okay. So the probability divided by 1 minus p, 1 minus the probability is 1,000. So let me give some examples. If suppose p is equal to 0.9. That means that the odds are 0.9 divided by 1 minus 0.9, which is 0.9 over 0.1, or 9. So those are large odds. If I take p equal 0.1, I'm going to get 0.1 over 1 minus 0.9, 1 minus 0.1. So that's equal to 0.1 over 0.9. So that's equal to 1/9. Okay. So large odds means high probability. And small odds means low probability. Okay. And the odds are always between 0 and infinity. Odds are always positive. All right, so I've associated with the probability a number between 0 and infinity. But what I want to do is associate a probability with a number between minus infinity and infinity. Okay. So these are 10 numbers, so I should say these are 10 real numbers, which are positive or negative. I want to associate these 10 numbers with a probability. Or I shouldn't say with a probability, I should say with probabilities. When I associate these 10 numbers with 10 probabilities, I should be more clear about that. So let's make sure that I've expressed myself clearly. Go back a little bit and make sure that we've made things clear. I should just rewrite that, I suppose. I want to associate these 10 real numbers with 10 probabilities. And probabilities are between 0 and 1, so I'm working up to how to get a number between 0 and 1. So if I take the log of an odds, that's going to be equal to log of p over 1 minus p. Now the logarithm of a positive number gives a real number. Okay. This gives a real number between minus infinity and infinity. All right. So what I'm going to do is I'm going to associate my neural network outputs with log odds. Okay. So that means that my output, my NN output, is equal to p over 1 minus p, is log of p over 1 minus p. Sorry. And I can solve this for p. That means I need to rearrange. So I'm going to get the exponential function of the NN output is equal to p over 1 minus p. And if I solve that, let's see, how is that going to work? Then it looks like I'm going to get p is equal to the exponential function of my NN output. This is an algebra problem over, and I think it's going to be over 1 plus the exponential output of the exponential of my NN output. Okay, so that's how I'm going to associate probabilities with my neural network outputs. And if you want some more information on that, you can look up Logit. Okay. Because that's what I want to do. I want to classify my digits, and I want to classify my output as the most probable digit. Okay. Okay. All right. Let me all right, I should say something about softmax. also, but I think I don't have enough time. But suffice it to say that this softmax function converts these numbers into probabilities. Okay. All right. So let's see what we have next. All right. So let's look at this. Okay. So you can see the output here. So these numbers are all probabilities. They all add to 1. And in this case, all the different classes, 10 different classes, have similar probabilities. There's not one that's much larger than the other one. In this case, the first class has probability of 0.14, which is only slightly bigger than the last class, which is 0.12. But this is to be expected because the neural network hasn't been trained yet. It has no way of distinguishing which class is better or not. So let's get down to the training. Let's see if we can get down to the training within the next 10 minutes. Okay. All right, now, if you remember in my talk, I talked about a loss function. So what you want to do is take your output and create a loss value from each output. And the loss value will depend on the difference between your prediction and the actual value. All right, so here's the loss function defined, and use something called cross entropy. All right, so that's another technical term, but the idea here is that this is a way of measuring the difference between your prediction and the value and the actual value of the digit. So let's go ahead and put this loss function in. All right, so now what you want to do is you want to train your model using this loss function. All right. All right. So this performs the complete training of the this does the complete training of the neural network. So it's going to use backpropagation to adjust the weights in all of the layers of the model. Now this may take some time. I'm not sure how long this is going to take. Looks like it's done already. All right. This one here says that you're going to do this training in 5 stages. All right, and so you run 1 stage, 2 stage, 3 stage, 4 stages, and 5 stages. Okay. I guess it's still going on. So here's where I guess this is where the actual training is taking place. Still running. Now notice how the accuracy has increased. After the first training, the accuracy of the prediction was 91%, and it's gotten up to 97%. So the training is doing better and better. Now here it's training on the training set. Now I did mention that in machine learning, it's not enough to train your model. You need to make sure that it also performs well on data that you don't train on. And in this case, you take a second set of data, which is either a validation set or a testing set. Now, I didn't talk about validation sets, but here, if you notice at the very top, Keras does give you a testing set for the MNIST data set. There is a testing set here. So there's a set reserved to test the model. Okay. So here we do the testing. And here we have accuracy. So the accuracy, Charlie mentioned the accuracy. Accuracy is correct predictions divided by total number of total number of instances. So so this model is quite accurate. Okay. So let's take a look at this if we want to do a probability model, and we can take a look at what the output here is. Okay, so in this case, for this one particular digit, we have very small probabilities for these. There should be one category with a very large probability. That's right here. This means that almost certainly the output is at 8, because this class is 8 and this class is 9. So you see all of these probabilities are very small. There's only one that has a significant probability that's close to 1. All right, now certainly I went over this very quickly, but hopefully you get some idea of the outline of the process of creating and training a neural network. The same process is taking place even with very complicated neural networks. You set up the neural network, you set up the training, you do the training, then you do the either validation or testing. And the programming commands are very much like this. So I think this is something that you just learn step by step. You can't learn everything all at once. And the more exposure you have, the more familiar it becomes. So I think I'm going to stop there. Thanks for your attention, and I hope that gave you some idea of how to